Okay, so right now I'm going to work through these problems that I assigned for homework the other day. And these problems they're not like assigned as far as you have to complete them. They're just more out there for you to kind of look through. Another chance for you guys to figure out how well you know the material. And so as I work through this, we're just going to go through 1, 2, and 3 of this problem. So the first thing I'm going to do is I'm going to sketch out my situation here. Here I have a mass tied to another mass. This could be like maybe they're two mountain climbers sliding down. This would be not a good situation for number 1 because it is frictionless, or your mu is equal to 0. So first step is I want to identify all the forces. I have Fg1, Fg2, I have my normal force, Fn, and so then I will set up my axes, x and y, and down here I also have my y now and x. So that is to say that this direction is the direction of my acceleration. The system will accelerate in this direction. So now that I have my axes labeled, I want to break up my forces into their components, Fg1y and Fg1x. So let's see here. It's everything now in the x and the y. The Fn is in the y direction. The Fg, and I'll put an Fg2, that's in the x direction. And you know what these masses are, but I'm just going to solve this symbolically. So the first thing I'm going to do is I'm going to sum the forces in the x direction, because that's the direction that there is an acceleration. So this is not 0 here, not 0, so I make sure that I include that. And so now I have, let's see, I have Fg1. Oh, well, it actually would be very helpful if I came up with a free body diagram. So let's take a step back, free body diagram. And I have Fn up. I have Fgy down. I have in this direction, I have Fg1x, as you can see right here. This is down. And I also have Fg2. And I'm not really sure what the magnitudes of these are supposed to be relative to each other. I probably have those flipped. So now let's go and plug in. So here I'm looking at the x direction. So this is the x direction, and all the forces in here are Fg2 and Fg1x. So I will write this as Fg2 plus Fg1x is equal to, and you have to ask yourself at this point, what masses are being accelerated? M1 plus M2A. So now I'm just going to divide these out, or break these down a little bit further. M2G, Fg is always equal to mg, and remember that you have to carry through your subscript 2 so that you capture the force on mass 2, plus m1g sine or cosine. If this is my angle theta, then this is always my angle theta tucked up in here. So that's the opposite side, so that sine theta is equal to m1 plus m2a. Right, so we're solving for a, so we just isolate a. So then a ends up equaling my m2g plus m1g sine theta all over m1 plus m2. Alright, so there, I've solved for problem, or the first section of this problem. Now I'm going to go on to problem number 2, right below this. I think I have enough room. And now I do have a coefficient of kinetic friction, which happens to be given as 0.5. Although I'm not going to actually plug that number in, I'm just going to do this symbolically. I can actually go back to my sketch and just include right here my friction force. going to resist the motion. And so over here in my free body diagram, I now include my friction force. So I will do the same thing. I will sum the forces in the x direction is equal to ma, and I better sum the forces in the y direction, but now that doesn't equal ma, so in the y direction these are going to sum to 0. Alright? Or they could be summing to ma and my acceleration is 0, therefore they sum to 0. So here we go. So I can actually come up here and I can look at what I've done before, and I can carry that down through. So I'm going to capture this part right down here and then pull it down, and I end up with m2g plus m1g sine theta. And the reason I can do that is this represents fg1x, it's still down, and fg2 still down, and now I have to include my negative ff minus ff, so this is in the upward direction, is equal to now my m1 plus m2a. And I'll deal with this in a moment. So I'll write this out again, m2g plus m1g sine theta minus mu, and it's mu fn. This is mu fn, roughness of the surface and the force between the surfaces. And so now I have fn, and my fn is going to be equal to my fg. Ooh, this is terrible how I've done this. Fg, oh, this is fgx, and this is fgy. So yeah, this wasn't laid out very well. So this is fgy. So my fgy up here is going to be equal to m1g cosine theta. So I'll plug that right back in over here. So I end up with m1g cosine theta is equal to m1 plus m2a. So now I solve for a again. A is then equal to this big mess here of m2g. Make sure I carry that through. This is the bookkeeping part of this problem. m1g sine theta minus mu m1g cosine theta all over m1 plus m2. And let's just double check, make sure I know all these values. I know m1, m2, that's given the problem statement. G, I would put in as 10. Theta is 30, so this becomes a half. I have all of these values. My mu is 0.5. And this is cosine 30, so root 3 over 2. And I know my m1 and m2, so therefore I can solve for a. And so now let's look at what's going on with problem number 3. Problem number 3, I'm allowing this mass right here to increase until it's not moving. So I have a coefficient of static friction. So as this gets larger and larger and larger and larger, eventually I'm going to reach a point where this is not going to slide. So again, if we go back to these two, maybe they're mountaineers, and one guy is holding on to another guy who has slipped off a cliff or something like that, and he wants to have enough mass and enough force to prevent them both from going off the cliff. And so let's figure out what this mass needs to be. So let's see here. I can use actually the same exact situation here, except the difference now is that for part 3 I have an acceleration which is 0, or that is to say that the sum of the forces in both directions is equal to 0. But it's the same free body diagram, and it's the same sketch that I see right here. Alright, so let's overlay this right here, and so then we end up with 3, we'd say the sum of the forces in the x direction is equal to ma, and this is 0. Well, that makes it a little bit easier. So let's see here. In the x direction, I end up with ff, fg2, fg1x. So these two, fg2 plus fg1x, is going to be equal to ff. And so that's kind of interesting. As my mass goes up, my fg1 becomes greater. But so does my fgy, that becomes greater. So therefore my fn becomes greater, and if my fn becomes greater, then my ff becomes greater. So I want this to grow more than my fgy grows and my fgx. And so let's see what happens here. So I end up with, let's see here. I'll actually look right directly at this, and I'll say that ff has to be equal to fg2 plus fg1x. So I end up with mu Fn is equal to m2g plus m1g sine theta. And so I need to go back here and look at what my Fn is. As we solved before, Fn, we said that is equal to Fgy, which is equal to m1g cosine theta. So let's plug that in. So I end up with mu m1g cosine theta is equal to m2g plus m1g sine theta. So I have a g in each term, so I can cancel those out. Can I cancel out my m's? No, because I have an m1, an m2, and an m1, so I can't cancel those out. So that's where it's important to carry through your subscript. And then let's see here, what's the problem? So we're trying to get our m1 to increase to the point where this will equal this value. So really m2 we want to kind of become fairly insignificant. So let's see here. So let's isolate m1. So let's pull m1 onto one side and m2 onto the other. So we have mu m1 cosine theta minus m1 sine theta is equal to m2. It'd be nice if we were solving for m2 at this point, but we're trying to isolate m1. So we end up with m1 mu cosine theta minus sine theta is equal to m2. m1 is then equal to m2 all over coefficient of static friction now, which was given in the problem, cosine theta minus sine theta. All right, so let's just play around with and see how these numbers work out. So we end up with, let's see here, will this actually work? Or have I given you a bogus question here? So we end up with m2, which, let's see here, I have to go back to my problem statement, and my m2 ends up being 3 kilograms. 3 over my mu, which is 0.8. Cosine of 30 is root 3 over 2 minus 1/2. Alright, so this number is clearly going to be greater. Ooh, I don't know. Let's see here. If I were to actually do the calculation, I end up with 0.8 multiplied by 1.7. Now this is where I could be wrong. 32 over 2 minus 1/2. Oh no, so I end up with a negative. Oh my goodness. I think this value right here is going to be greater than this value right here. So therefore this ends up being negative, so that means no matter what I do to m1, I'm never going to get it to a point where I can prevent them from going over that cliff. So this was a bogus question, so I apologize for that, but at least we were able to work through this. If I either gave you a higher mu static or a lesser theta, then this problem would work out. At least I think I've done this right. Double check my work up here. Alright, so that's it for now. Hopefully this is helpful.